Hello and welcome to today's video where I'm going to do an introduction of this next section we're going to get into, which is proofs. This can be a really tough section for some people, and it can also be really easy for others. Some people really like proving things. They like the logic of going through step by step and trying to get to a conclusion. Others just want to do the numbers. They're not a fan of this, but really there's something for everyone in this section, so hopefully you can get something out of it. There's a lot of different methods for proof that we're going to cover here, and I'll talk a little bit about them right now. First, the introduction to proofs. There's some vocabulary you need to know. First is the definition. That's something given to you. You don't need to give a reason as to why it's true. We assume it's like universally accepted. So a squared plus b squared equals c squared. That's the Pythagorean theorem. That's a definition. You don't have to show that. And that's a theorem. That's something to be proven. So you have to, that's what you're trying to work for. And it typically results in corollaries, which are basically things that result from the theorem. So really closely related to the theorem that you've proven, but not the exact thing. And then another important term is parity. And this means that two integers are of the same parity if x and y are both even or they're both odd. So we say that integers are of opposite parity, of course, if one is even and one is odd. So just know that term because that shows up a lot in proofs. They might say, well, if they have the same parity, is this even or odd? So you need to be able to tell, well, what does it mean that they have the same parity? And that just means that they have the same even or odd status. So common types of proofs. So these are the ones that I'm sure you might have done some of these before, but just the basics here. So direct proofs, if P then Q, that's the most basic thing. You directly try to show that, well, if P is true, Q must be true. The thing is with direct proofs is you can't do them all the time. They're going to throw tricks in there to just make it to where you can't just directly plug in whatever P is to arrive at Q. Next, we have proof by contraposition. This is a common one where if we're trying to prove P and then Q, we can do this with contraposition by proving not Q implies not P. So remember, in our logic section, we did not P implies not Q. That's equivalent to P implies Q. They're logically equivalent. If you want to do a truth table, you could do that and you'd see that they're the same. So that's another way to do a proof. We can just do the contraposition here instead of, actually, wait, this should be not Q implies not P. Misspoke there. So not Q implies not P. So that's the contraposition. So sometimes that's easier. Sometimes it's easier to say, well, what if the conclusion is just false? Can I easily show that the hypothesis is false? And that can definitely happen sometimes. And if you wanted to do a statement, truth table, you could. And I almost recommend it just to make sure you feel good about contraposition. So next we have proof by contradiction. Here we assume the logical negation of the result, and then we reach some kind of contradiction. So we assume the opposite of what we want to prove. So we kind of assume not Q, and then we show why P just can't happen. So it's used to show the impossibility of something. You assume it is possible, and then you reach some contradiction. So you use this for things like proving rational and irrational numbers. This, so that can be a harder one. I think proof by contradiction is one of the tougher sections of this unit, but we have some examples and you'll feel good about it by the end. And next we have proof by cases. So sometimes when we're trying to prove directly P implies Q, it can be easier to use a disjunction where I can prove, well, P1 or P2 or all the way to PK instead of using P. And this is common when you kind of have like if n is an integer, then this happens. Well, there's two cases where n is an integer. It can be an even integer or an odd integer, right? So if it's easier to show that, well, when it's even, this happens. When it's odd, this happens. Then it must happen all the time. So that's a common thing, and this is a good one to know. Proof by cases. Most teachers cover it. Some don't, and the ones that don't, I think, really are doing a disservice because they can really make you do some of these a lot quicker, and they can make more sense. So basically, this you'll see some examples later on, but this is a good way to do some proofs. And then we also are going to cover mathematical induction. This is kind of a proof method. It's kind of something used within proofs a lot. And this is a common tool for just showing that, well, if this happens, then this has to happen for all cases. So what you do is you show the base case. You show that, well, the first thing is true. If it works for n equals 1, and then I can show that it works for n equals k plus 1, then I can show that it works for everything. So the logic, we'll get into this much more in the actual video, but the logic is with dominoes. So if the first domino falls, and then I can say, well, the second step would be when any domino falls, the next domino falls. So notice that I've said the first domino fell, and I say that when any domino falls, the next domino falls. Well, if the first domino fell, and when any falls, the next one falls, I know the second one fell, which implies the third one fell, and you can go step by step all the way to assume all the dominoes will fall. So that's kind of the logic of mathematical induction. Hopefully that makes sense. We'll get into a lot more with that. And mathematical induction can definitely be one of the harder parts of this course. So definitely pay attention to that video. Then lastly, just some things to know. So how to write odd and even integers within proofs. You may know this, but if we have an odd integer, we want to write it as 2k plus 1, where k is an element of z, which means k is an integer. Just the common way to write the odd numbers. Then for evens, we just write it as 2k, where k is an element of z again. And the reason we do that is just because it's the simplest way to write them, and then we can, from there, we can plug them into all kinds of formulas and things like that. You're going to see that all the time. Then the divisibility symbols and rules. This one's a little less intuitive, but so for any integers a and b with a not equal to 0, we say that a divides b, or b is divisible by a, if there's an integer c such that b equals ac. So that seems really confusing, but basically it's written as ab, so a divides b. That's what you need to read this as. A divides b. You will sometimes see this in proofs. So let's look at an example. So does 2 divide 4? Yes, it does, right? Because 4 divided by 2 is 2. Does negative 2 divide 8? Yeah, it does, right? Yes, and the answer would be negative 4. So I can do 8 divided by negative 2. An example of when it wouldn't work would be, does 3 divide 4? No, it doesn't. It equals a decimal. So it only works if there's an integer c such that b equals ac. And in this case, it would not be an integer. It'd be a fraction. So hopefully that is a quick intro to proofs. We're going to do a lot of examples later on. I just wanted to kind of get you comfortable with all the terms that you will be seeing throughout this unit. So thanks for watching, and I hope you enjoy this section.